Let's move into data ingestion and output, or data in and output in Python. The question we're trying to answer is how you can process your data and preserve the results of your work. So far, you've been writing programs that generated perhaps some output to the screen, which is the end result. But all of that was gone when your program execution finished and you shut down your browser or your browser tab. And the next time you fired things up, it wasn't there anymore. Also, perhaps you want to be able to dynamically adapt your processing depending on what kind of input comes in. So let's look at the data processing pipeline here. So far, we've mainly dealt with the data processing workflow, where we turn boxes from our flowchart into algorithms, into functions, little sub notebooks. We haven't really dealt much with the data output side. So where do our results end up in? Or the data ingestion, where do data actually come from? And how do we get those data from the source into our workflow? So let's first talk about data storage. Storage needs generally range from a single file with a handful of rows and columns to data distributed over millions of files, each with massive amounts of data. We've dealt with the first part in our examples already, small files, small examples. The second part, millions of files, think about YouTube and all the videos that are on there, how they might be stored, and how you might be able to run analytics over all of these. The famous examples of getting machine learning algorithms to understand whether there's a cat or a dog in the video. If we bring it a little closer to home, if we think about geophysical sensors, for instance, or other geosensors that are distributed, say, in the entire state of Alaska, in the US, or worldwide, each of those might create a file with a handful of rows and columns on the grand scheme of things. But you will certainly want to process all of these data with a single program, right? Be it ingestion just for plotting, or some higher order analysis, simple time series statistics, or more complex modeling tasks. Consistent formatting is difficult for people, though. You have to think very hard about the format initially if you are in charge of it, or sometimes you are not in charge of the original data, but you store intermediate results. Sometimes your code evolves and you think, oh, I want to change that format. Think about what the downstream effects of that are. Sometimes you change format, and then you have two sets of files, some with the old format, some with the new format. Now, whoever is the unlucky person to ingest your files has to update their reader and accommodate two different formats that have to be ingested. So it is important to initially think hard about the format and think about the use cases that the output that your program is generating should serve. I'm sure you're aware that data are generally stored in vast ranges of different data formats. There are two main categories: text-based, for instance, the modern Excel files, the XLSX files, other tabulated data, CSV or text. And then there is binary data storage, old Excel files, XLS files, or HDF5, H5, or NetCDF, and some other formats. The main difference is that text files are human readable, binary files are not. A human readable file has the benefit that you can always fire up a text editor and look at the file, figure out the format, and write a reader. Binary files, it's a little bit more complicated. So let's think that you want to write a program that takes in some data, some file. What are some of the questions that you should ask? Well, first, what is the file format? Is it binary or is it text-based? Is there a reader for that specific format, for instance, XLS files? And then what is the data structure that this reader is generating? How can I then access the data in that data structure inside of my code? How will I access data point X? These tools have documentation that you should be aware of and read and become intimately familiar with the tools that you're using. A question that you should also ask on top of this, perhaps it's something that you actually need to explore through a reader if you can't look at the data directly, is how the data are structured in a file. What variables and parameters are in there? Does it come with any metadata? So in a text file, this could be some header information. What is metadata? It is data that describes the data. You can think of an instrument measuring the water level in a river, and the data observations are a table with 2 columns, time and river water level. The metadata then describes the geographic location of it, perhaps some information about the instrument itself. What is the manufacturer? What is the software version? Something about the operator, who to contact if you have questions about the data. All of that is metadata that is incredibly important, even if perhaps it gets into the way of easy reading of such a text file. And then what are the value types? Is it all floating point values? It's important to know what these things are so you can convert them into something that you can handle easily internally in Python. If nothing exists for you to read your data with, you may have to write your own reader for specific formats. There are modern tools in NumPy and Pandas that make that easy. It can be one function call or just a few to at least read the next line of a file and then kind of split things up into variables. On the output side, we have fairly broad range of possibilities. We write something to the screen. That's what we've done a lot already. You can store your results in a file on a hard drive, in the cloud, everything's a hard drive, or you can make a plot. You may not want to store the numerical values of something, say of a simulation, but all you want to get out of it is a plot. That too is data output, and then that plot gets stored. Plotting comes a little bit later. Today we'll focus on point 1 and 2 here. Output to the screen can be extremely effective. I mentioned that already. You can read it right away. That is easier. The smaller your volumes of output are, you can easily get overwhelmed with too much output. And as I said, you may be able to pipe the output into another program. More about that in Unix tools. You can also redirect the output that goes to the screen dynamically into a file, which some operating systems allow you to do. So even though the program thinks it should be all on the screen, you can say, no, I want it in a file, and you're redirected. Output to files should happen if the computations take a long time, say for modeling, right? If your program runs for hours, you probably want to store the results if you want to do something with them afterwards, say make a plot. So you don't always have to run your entire code just so that a plot that looks exactly the same as previously because you didn't change any parameters gets regenerated. The same thing for data formats apply as for data reading, right? You should think whether it should be text-based, binary, how you are the consumer of your own products, how you want to most easily deal with them. You should put effort into keeping documentation with the data. That means metadata that could be in header lines. Some data formats are self-documenting, where variable names are included that could carry some meaning. Try to avoid having a huge data file with nothing in it but numbers that will not tell you what's going on. You should think about trade-offs between the long-term readability of your file. So text files will always be readable. Binary might not if you lose the format. Proprietary data formats, will you be able to read some Excel file in 30 years? And the storage efficiency. Is it important that the file is 2 or 5 megabyte? Should it be rather 500 megabyte or is 5 terabyte okay? Text files tend to be less efficient in their storage. That is a trade-off between being able to read it manually. The last word here on the command line. There are excellent time-tested tools available for really efficient processing of large quantities of especially text-based data on the command line. It's an entire book that was put together by Jeroen Janssens, data science at the command line. We'll talk about a lot of these tools in a later portion of the course. I list this here for completeness. There's a link to the free online version of this book.